And oh, this sounds better. All right. So we have seen this example, which tells us that if we want to verify controllability of the unknown truth system, we do not need data to be informative for system identification. Let's go through the proof or parts of the proof of the theorem to give a flavor of type of arguments used. Well, if part is easy again. If this matrix has full row rank for all lambda, I can take one data consistent system, an arbitrary one. Then I know that this linear equation is satisfied by the definition of data consistent systems. Now, if I add both sides minus lambda times x minus, I can write the right-hand side in this way, which tells me, since this is full row rank, which tells me that this matrix must have full row rank. And then by the how-to test, then AB is controllable. This is the easy part. For the only if part, I will assume that all data consistent systems are controllable, and then I want to show that this matrix has full row rank for all complex lambda. Okay. So all data consistent systems are controllable, and my goal is to show that for arbitrary lambda and arbitrary complex vector z, z conjugate transpose this matrix equals 0 implies z is equal to 0. Or in other words, this matrix has full row rank for any lambda. Okay? So I'm going to look at the case where lambda and z are real, and non-real case is similar, but it takes more space, so I skip it. It is in the lecture notes. But the main idea is here in the real case. So now I take a real lambda and a real vector z such that norm of z is 1. Okay? And I assume that this relation holds. Z transpose times this matrix is 0. Okay? I take an arbitrary pair, AB, data consistent. What I know is that this AB is controllable because all of them are controllable. Now, if I look at Z transpose x plus minus lambda x minus, I can replace x plus by a x minus b u minus, and there is the minus lambda x minus part. So this expression is equal to this one, and it is 0. Okay? What does that mean? Now, if you look at this expression, I have Z transpose times A minus lambda I, so it is here. And Z transpose B times U minus, so it is here, right? If I look at this expression then, these Z-related terms are going to cancel out because of this relation. Therefore, I'm going to look at A times x minus plus B times U minus, and it is x plus. Because AB is in the data consistent set. So this is x plus, which means that this pair is another data consistent system. Agree? I started from a data consistent system, AB, and data consistent means that, oh, this is Henk from yesterday. And this is the definition of data consistent system. AB data consistent means that this linear equation is satisfied. So I take one of them using the property that Z transpose is a left annihilator of this matrix with lambda. I came up with another one. So this new A, this new B is another data consistent system. Right? So this pair is another data consistent system. Okay? Therefore, it must be controllable because all of them are controllable. Let's look at now Z transpose times this new A. Well, Z transpose Z is 1. Right? Therefore, this is going to be equal to lambda times Z transpose, because I have Z transpose A here. Z transpose Z, Z transpose A is going to be also Z transpose A, so they cancel each other. And then I have minus minus plus lambda Z transpose. Which means that lambda is an eigenvalue of this matrix. Okay? Let's look at Z transpose times B new B. Well, Z transpose Z is 1. Therefore, this thing is going to be 0. What does this tell us? Well, because of Hart's test, it says Z must be 0, because this pair is controllable. If Z were not 0, we would contradict controllability. But Z0 is contradiction because Z transpose Z is 1. Therefore, we prove that this implication holds. So this matrix x plus minus lambda x minus must have full row rank for any lambda. Okay? So this is a necessary and sufficient condition for informativity for controllability. If lambda happens to be a non-real number, then there is a similar construction here, which is a little bit more complicated, and it is because of the fact that when I defined, I didn't write it explicitly, but I consider only real matrices A and B. The similar construction with complex Z and lambda would work, but yield complex matrices, which I do not consider as data consistent. So if lambda and Z are non-real, there is a way to generate data consistent systems, real matrices, but it's a little bit more complicated than what is it on the slide. Okay. Now, here is the question. Well, Hartus test is about finitely many lambdas, eigenvalues of A, at most n, if A is n by n matrix. Whereas this test requires checking full row rank of this matrix for every complex number lambda. Huh? Well, there seems to be a way to make it finite. I'm not going to prove it, but we can prove that the data are informative for controllability if and only if X plus has full row rank, and this matrix has full row rank for all mu eigenvalue of X minus X plus dagger, a right inverse of X plus. And you can see at least A from the theorem very easily, because if this has full row rank for all lambda, in particular, for lambda to be 0, it has to have full row rank. And in that case, X plus must be full row rank. Huh? And the rest is, the rest follows from simple algebraic manipulation. Okay? So now, this is finite now, because I can first check whether X plus has full row rank. If not, end of the story. If yes, I find the right inverse, find this matrix, find the eigenvalues, and check this rank condition on the eigenvalues. It is legitimate then to call this as data-driven Hartus test. Huh? Well, once we studied controllability, I can define the similar concept for stabilizability, informativity for stabilizability. All AB pairs need to be stabilizable, and then I very similarly can prove this theorem that stabilizability is a necessary and sufficient condition for informativity for stabilizability, is that this matrix must have full row rank, not for all lambda, but for all lambda outside the open disk. Okay? And again, one can make it a finite, one can come up with a data-driven Hartus test. It is a little bit more complicated, but essentially it is the same idea. And again, also for stabilizability, one doesn't need identifiability. I can, if the data are informative, I can guarantee stabilizability of the true system, even if I cannot identify it. Okay? Any questions? How much time do I have still? One hour. Okay. Because I am halfway through. Half an hour wouldn't be enough. All right. But I think I have enough material to cover an hour. So far we have seen stability for autonomous systems and controllability for input state systems. Okay? Let's look at stability again, but not for autonomous systems, for input state systems. So this is the setup again. I have a true unknown system, ASPS. I collect data from input state data from this system. I write the set of data consistent systems. And this time, I am interested in informativity for stability of input state data. If it were only state data, I already know the answer. But this time, I have also input data together with state data. Well, I'm not going to prove every single statement, by the way, because it would take very long. but I want to give a flavor of different types of properties. Then one can prove that the input state data are informative for stability if and only if X minus has full row rank and there exists a right inverse of X minus such that X plus, X minus dagger is stable and U minus, X minus dagger is 0. If these conditions are satisfied, then A is uniquely determined by the data, but B may not be uniquely determined by the data. So basically this theorem says for stability in the input state data case, one can verify stability without being able to identify the system again. Because we have more data, we have also input data. So it is in contrast to only state data situation. And if we remember the condition for identification in the input state case, it was X minus U minus having full row rank. And as you see, this doesn't need to be the case for informativity for stability. Only X minus needs to be full row rank. And you see that there are more properties than controllability for which we can guarantee the property, although we cannot identify the underlying system. At least for controllability and stabilizability and stability, we established that. But these are all, of course, analysis problems. Okay? If we continue with analysis problems, we studied controllability, why not observability? So now I change the setup to state output data. I have state output system, no inputs. N is the dimension of states. P is for the outputs. I have a true system in this model class given by matrices AS and BS. These are unknown. I collect data, let's say state data and some output data. I write the data then they have to satisfy these relations with respect to AS and BS. I then write down the data consistent systems. These are all CA pairs satisfying this linear equation. Right? You see, we can deal with pretty much anything. You can write down these things. Whether they lead to something interesting or not is another question, but we have a framework in which we can formulate all sorts of problems. Okay? Any questions here? Then, I know that the true system is one of the data consistent systems. What about system identification in this case? Whenever I change the model class, the type of the data, there is another system identification problem. Okay? Well, one can show that also it's clear from here because AC are the unknowns. This has a solution, but it can have a unique solution only if and only if X minus has full row rank. So system identification is going to boil down to X minus having full row rank. Okay? What about observability? I'm going to say that the data state output data are informative for observability if all systems in the data consistent set are observable. It turns out that stable, spectral radius needs to be less than 1 for any alpha. If I take the limit alpha tends to infinity then, this expression needs to tend to 0 because m alpha, spectral radius is less than 1. 1 over alpha, alpha tends to infinity, goes to 0. If I look at the limit of this thing divided by alpha, alpha tends to infinity, I obtain this expression. Again, the transpose is on the parenthesis. So I have here a matrix transpose times the matrix, and it is spectral radius is 0. Now this is a symmetric matrix, semi-definite matrix, spectral radius is 0. This can happen only if the matrix itself is 0. And so, therefore, for any A0, B0 with this property, A0 plus B0, K needs to be 0, where K is a stabilizing feedback. And from that, we see that this implication holds now. Whenever A0, B0 kills X minus U minus from left, it kills identity K from left. But now, some of our colleagues like to drop names from Roche-Capelli. What is it? Roche-Capelli theorem. It follows, no, it's a basic elementary fact from linear algebra that if this holds, identity K must be equal to X minus U minus times some matrix, let's say F. And if it is so, if you look at the first row block, identity is equal to X minus F, means that X minus has full row rank, and F is a right inverse of X minus. And then from the second one, we also see that this X plus times F is A plus BK, and that is stable, which proves first A and then B. Okay? Any questions? But now I have a question. It is nice, but is it useful? Forgetting about practical issues, is it useful from theoretical point of view? It's not so useful because it says there exists a right inverse. How am I supposed to check these conditions? If the inverse is not unique, then there are infinitely many inverses, right inverses. And I have to find one such that X plus times that right inverse is stable. And that is not an easy problem. So we have to do something for that. Well, one can actually come up with linear matrix inequalities which are going to replace these conditions A and B. I'm not going to prove these statements, but one can prove that informativity software to solve linear matrix inequalities and then solve these ones. But there is a catch still. Look at the dimension of theta. Theta has T rows, so this is the number of data samples, and n columns, that is the system dimension. So if you have a very large data set, the number of unknowns is very large because you have n times capital T unknowns in these NMIs. So if you have a very large data set, it is going to be more difficult to solve these LMIs. Therefore, somebody should do something better. And there is indeed something better. Another LMI, positive definite P, positive alpha, some L, and this is the LMI. And as you see, P, alpha, L are unknowns. All the rest are data matrices. Huh? And if these LMIs are feasible, then LP inverse is a stabilizing feedback. But let's now count the number of unknowns. Huh? The number of unknowns now does not depend on the data size, but depend only on the system size, the number of states, the number of inputs. Huh? And you cannot go beyond that because already the size of the system, of course, limits the number of unknowns. Huh? So imagine if T is very large, this is going to be much, much larger than the number here. So these are even more friendly LMIs. But basically then, if this door is open, somebody rushes in, says, okay, I have this data, can you please, I just open my laptop, write down this LMI. If it is feasible, I am there. If it is not, then I try to calm the person down, like, sorry, we cannot find a stabilizing feedback. So this was about stabilization. Now, as I said before, per problem, conditions on data change. Well, we have seen it in the analysis part. For different problems, we have different conditions. Sometimes identifiability is required. Sometimes it's not required. But basically, per problem, we study data informativity. Now, I'm going to study linear quadratic optimal control because there was a request, and I typed these slides in the break. No, I already had typed them. But there was a question about LQR. So first, I want to explain the optimal control problem I want to look at, because there is also a misconception among control people that LQR is very easy and there is a unique solution for the Riccati equation and so on and so forth. Sometimes even in textbooks it is written in that way, but it is not so. And the data part is going to be quicker. But let me explain what I mean by what kind of LQR problem I'm going to look at. I start with a linear input state system, and I have this cost. Q is semi-definite, symmetric semi-definite, R is symmetric positive definite. And as you know, the idea is to minimize this cost. But there is a very important issue. It depends on whether you require, the solution of this problem depends on whether you require X tend to 0 asymptotically or not. So I'm going to look at the zero endpoint problem, in which not only I try to minimize this, but I have this extra constraint that X tends to 0 as T tends to infinity. If you drop this assumption, then it's a different problem. And in principle, these two problems do have different solutions. That is a point that is missed very often in the literature. So I look at LQR with 0 endpoint. X tends to 0. Okay. I want to minimize it. Well, we study LQR problem in continuous time. This is a discrete time version, but you wouldn't be shocked if I tell you that it is a Riccati equation that needs to be solved. So then this LQR problem with 0 endpoint is solvable if and only if AB is stabilizable, some observability condition of QA on the imaginary, on the unit circle, sorry. And if these are satisfied, then one can prove that there exists a unique, largest positive definite solution, P plus of this discrete time algebraic Riccati equation, in the sense that P plus would be greater than or equal to P for any real symmetric P satisfying the Riccati equation. And for every x0, there is an optimal input U star, and it is given by this feedback law where K is computed from the solution of algebraic Riccati equation A, B, and R in this way. And on top of it, A plus BK is stable. These are all from the model-based theory and nothing to do with data-driven yet. It's a recap of LQR with 0 endpoint.
What is largest positive solution?
So it is largest in this sense. It may have multiple symmetric solutions, and P plus is the largest in the sense that P plus minus P is semi-definite. And it is unique. And I'm going to say that LQR, ABQR is solvable. If it is solvable, I'm going to say that K is optimal feedback gain, K given by OFG here. Okay? And again, I start with the usual setup, input state system, input state data. This is the set of data consistent systems. The true unknown system is one of them, but there may be many. And I define now the data to be informative for optimal linear quadratic regulation, as I defined in the previous slides, if there exists a K such that this K is optimal feedback gain for any AB. Q and R are fixed. So if this K solves the optimal control problem for every AB data consistent. Okay? So what is your guess? Do we need system identification or identifiability or not? Yes, there is an observability condition that needs to pop up, show up itself, show itself in the conditions. That's a very good guess, because it was not a yes/no answer. The answer is in the middle, and indeed A needs to be identifiable. Yes, very good intuition. The data are informative if and only if one of the two following conditions hold. This is really, in a way, interesting, because I have never proven anything in my life with this kind of flavor. Two conditions, one of them needs to hold, and they are also completely apart from each other. The first one says that the data are informative for system identification, but then we are done, right? And the second one says that A part needs to be identifiable. B part does not need to be identifiable. But there are more. AS needs to be stable, and Q times AS needs to be 0. And in that case, K is 0. But I have to say that this B is a little bit of, it is a pathological case. And it is because of something deeper sometimes we forget. Some of the discrete time systems you cannot obtain as discretization of continuous time systems. If you use zero-hold discretization, in the discrete time, A matrix would be always non-singular. Huh? But if we start from a discrete time system, we do not impose that. Therefore, we are looking at a larger class of systems than one can obtain as a discretization from continuous time systems. And that is, this is exactly because of that, I believe. Okay? And how do I prove it? I'm not going to prove this because this really takes some time, but I can tell you the crux of the proof. The crux of the proof is, well, for given AB, I can write the algebraic Riccati equation. Huh? And since K needs to be the same for all AB, one can prove, this is the K, one can prove that this solution of the solution of this algebraic Riccati equation does not depend on the choice of AB. That is the crux of the proof. Once it is proven, the rest is easy. Okay? So I have another R, right? I have 4 more slides left. Okay. There is one more thing I want to say about optimal control. Of course, this doesn't say how we can find the K from data. Well, you can write a semi-definite program to find K. You can try to maximize trace of P subject to these constraints. This has a unique solution, and it gives you the solution of the algebraic Riccati equation. And the nice thing is, this depends on the data only. And I don't have A, B, I have the data. So this is the way to solve optimal control problem. Okay? And if there is a P plus, then you choose K in a certain way. Okay? Now, here is what we have done. On the we are interested in exact data to begin with. On the analysis side, we looked at stability, controllability, stabilizability, stability again, but with input state data, observability. And on the design side, we looked at stabilization by state feedback and LQR. Huh? But there are many more, even more than what I listed here, problems which are solved in this framework by us or by others. Huh? And this is a partial list of all these problems. In the lecture notes, you see you can access most of them. By the way, it would be nice if we have an email list for all the participants, because soon, in a month or 2, we are going to finalize the book, and then we can share the entire book. What we shared is part of the book, a large part, but nevertheless not the complete book. Okay? And so one can look at suboptimal problems, optimal control problems. One can look at stabilization by dynamic feedback, and this is the data type. I was interested in input and state data, but one can look at even input-output data. So you can do whatever one can do in model-based theory in this framework for data. Okay? But as I said, this was about exact data. So the last bit of today's presentation, I want to give an overview from mathematical point of view to connect it to noisy data. Let's think about input state systems. So we have this set of consistent systems, data consistent systems. In the exact data case, this set is an affine set. It is a set of solutions to a linear equation. It is a vector in this space. This belongs to Rn times n cross Rn times m. If you treat this as a vector space, this is just one element of it. And this set is going to be then one vector plus a subspace. If I depict it in 2 dimensions, of course it is not fair. It is going to be something like this, a shifted subspace. Okay? So essentially in data informativity, from mathematical point of view, what we do is to find conditions under which this affine set is included in another set. For instance, in the set of all controllable systems for controllability. But all controllable systems have an interesting geometry. They are not convex, they are dense. And it seems that it is possible that a affine space can be in that set. But when it comes to design problems, then it is not about a B set, but there is also the K. If you fix K and look at A plus BK and require A plus BK to be stable, that is not even a convex set. But we want this affine set to be in that convex set parameterized by K. For each K there is one, and we want to put this affine set into one of them. And it is possible apparently only if that A plus BK is a singleton. So this is the way one can look at from mathematical point of view. For the exact data, set of data consistent systems is an affine set, and depending on the problem, I have another set, and I am trying to figure out conditions on data so that this affine set is included in the other set. Okay? And it requires different type of, it requires a certain type of mathematics. As you can remember from the proofs, I take a data consistent system and create yet another one, actually a bunch of them with a parameter alpha, take alpha to infinity and so on to make conclusions. That's the type of mathematics we used so far. When it comes to noisy data, we are going to look at a setup of this form, again, in state input systems. But we are going to add a noise term. W. Well, true system is unknown, but also the noise is unknown. Obviously, one cannot do anything without assuming something on the noise, because if noise is arbitrary, every system is a data consistent system and there is no hope. So what is a reasonable assumption on noise then? Well, I would say something like an energy bound. If I collect all these unknown noise terms, W in a matrix W minus W minus transpose less than or equal to some positive number times identity means that the noise samples are small. Okay? I can write down then this relation now, and Henk is going to, of course, go over the details. I'm just giving a flavor for tomorrow's lectures. Then I can write these data consistent systems. But the required mathematical tools are different now because these systems are going, these sets are going to be ellipsoids rather than affine sets. So one needs to develop some tools for in which we have these ellipsoids, and then they are included in other sets. So that is going to be that's going to be the high-level explanation of noisy data, but we will see the details tomorrow. Any questions?
In the LQR case that you did, that was a direct approach, right? The LQR controller that we showed, that was a direct approach.
Yeah.
But you could, so you formulated that as an optimization problem. But you could also do an indirect approach because the condition, the identifiability condition has to be true.
Yeah.
And so then you could replace A and B in that expression for K
Yeah.
by their data-driven equivalent.
Yes. Yes. True. I mean, true in the sense that this B is a pathological case. If I forget about B, then of course it says you should be able to identify the system. Then I would identify first and solve the Riccati equation. But if I want to treat both A and B, although B is a very pathological case, if I want to treat them equally, then I can also alternatively solve this optimization problem. But I mean, LQR is not an interesting problem, that much interesting problem in terms of data-driven control. Everyone is hungry, of course. All right. Thank you very much.